in this lecture we'll find out the radius of the circle using two different methods. In the drawing we have a circle. We know that the center of the circle is at this point O. We also know that the length of line segment AB is equal to 6 units, line segment AD, this line segment equals to 18 units in its length, and finally line segment BC equals to 13 units in its length. And we also know that this angle BAD equals to 90 degrees, and this angle ABC, it is also equal to 90 degrees. Our mission is to find out the radius of this circle. So first of all, we will make a construction. That is to say, from point C we will go perpendicular on AD. So actually this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. By this construction, we actually created a quadrilateral ABEC. This quadrilateral has 3 right angles. The sum of 3 right angles is 270 degrees plus the missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here, the fourth angle, must be also equal to 90 degrees. So inside quadrilateral ABEC we have 4 right angles, and therefore quadrilateral ABEC that has 4 right angles we relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6 units according to what is given as the question, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE, but BC equals to 13 units according to what is given as the question, therefore AE must be also equal to 13 units. And what is the length of line segment AD? From the drawing it is very easy to see that ED equals to AD minus AE. Again, ED equals to AD minus AE. That is to say, ED equals to AD, that is 18, minus AE, that is 13. 18 minus 13 is 5. Okay. In the next step, we will join points D and C together by a straight line. By joining points D and C, actually created the green right small triangle EDC. In the next step, we will implement the Pythagoras theorem on the green small right triangle EDC. On the right green triangle EDC, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green right triangle is DC, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. So DC square, that is the square of the hypotenuse, the green triangle, equals to EC squared. EC equals to 6 units. Therefore, EC squared is 6 squared, that is 36, plus ED squared. ED equals to 5 units, as you can see here. Therefore, ED squared equals to 5 squared, that is 25. In conclusion, we found out that DC squared equals to 36 plus 25 is 61. So DC squared equals to 61. Here we take a root out of this equation and we'll get that DC, that is the hypotenuse of the green right triangle, it is equal to the square root of 61 units. So I can write here that DC equals to the square root of 61 units. In the next step, we will join points B and D together by a straight line. By joining points B and D, we created the right big triangle ABD. In the next step, we will implement the Pythagoras theorem on the right big triangle ABD. In the right big triangle ABD, by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD. Therefore, the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus AD squared. In conclusion, according to the Pythagoras theorem, we found out that in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse, equals to AB squared. AB equals to 6, so AB squared is 6 squared, that is 36. Plus AD squared. AD equals to 13, therefore AD squared is 13 squared, that is 324. In conclusion, we found out that BD squared, that is the square of the hypotenuse, equals to 36 plus 324, that is 360. In the next step, we will substitute 360 by 30 times 10, by 36 times 10. So BD squared equals to 36 times 10. In the next step, we'll take a root out of this equation and we'll get that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we can take out from the root 36. And we get that BD equals to 6 times square root of 10 units. So we actually found out that the hypotenuse of the right triangle ABD equals to 6 times square root of 10 units. In the next step, we will find out the area of triangle BDC. The green triangle, triangle BDC. Actually, we know that the area of any triangle, and especially triangle BDC, the formula for the area is the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of the green triangle BDC, here the squared brackets is the sign for the area. It means the area of triangle BDC equals to the base of the triangle. We will choose the base of the triangle as BC, it's the side BC, times the height to the base, times the height to the base over 2. So here we will extend the base BC by a straight line, and from point D we will draw perpendicular on the extended BC. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point D and the extended BC as F. So you can see here the DF indeed creates 90 degrees with the extended base BC, therefore DF, it is absolutely definitely is the height to the base. So we have to find out the value of DF. So in order to find out the value of the height DF, we will focus on the new quadrilateral that we created here, quadrilateral ABDF. In this quadrilateral we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees, and because of the fact that quadrilateral ABDF has 4 right angles, quadrilateral ABDF is a rectangle. Quadrilateral ABDF is a rectangle but we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. So I can write here that AB equals to DF, and it is given as the question that AB equals to 6. Therefore we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. DF equals to 6 units, that is to say the height to the base equals to 6 units. Now we can easily find out the area of the green triangle BDC. So the area of the green triangle BDC will be equal to the base BC, but the base BC equals to 13 units, so we'll substitute BC by 13 times the height. We just right now found out that the height to the base, it is equal to DF, that is 6 units, all divided by 2. 6 over 2 is 3, and 3 times 13 is 39. So we actually found out that the area of the green triangle BDC, it is equal to 39 square units. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So this will be Rule number 1. According to rule number 1, if triangle ABC is blocked by a circle, so first of all I will draw the circle with triangle ABC. So this circle could be any circle. The center of this circle is at this point O, and we have triangle ABC that is blocked by this circle. This is triangle ABC. We'll define the radius of this circle as capital R. Here OM, this is the radius of this circle, will be defined as capital R. So here we have a triangle ABC that is blocked by this circle. Why triangle ABC is blocked by this circle? Because of the fact that all the three vertices of triangle ABC are touching the circle, different points. This vertex touches the circle at point A. This vertex of the triangle ABC touches the circle at point B, and this vertex touches the circle at point C. So only if all the three vertices are touching the circle at different points, only then we can say that a triangle is blocked by a circle. Okay, so if triangle ABC is blocked by a circle, then and you also know that the length of side AB is equal to A units, side BC equals to B units in its length, and side AC equals to C units in its length. So the radius of this circle that blocks the triangle ABC, so whenever you have a triangle that is blocked by a circle, you can use rule number 1, that is to say you can find the radius of the circle that blocks the triangle. So here the radius of this circle that is equal to capital R will be equal to A times B times C, that is the multiplication of the side lengths of the triangle ABC by each other, over 4 times the area of triangle ABC. Okay, here the squared brackets is the sign for the area, it means the area of triangle ABC. Okay, so we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle, triangle BDC, that is blocked by this circle. Why it is blocked by this circle? Because of the fact that all three vertices of this triangle are touching the circle at different points. This vertex of triangle BDC touches the circle at point B. This vertex of triangle BDC touches the circle at point C. And finally this vertex of the green triangle BDC touches the circle at point D. Therefore, we can definitely say that the green triangle BDC is blocked by this circle, and for that reason we can implement here rule number 1. So I write it down. The green triangle BDC is blocked by the circle, and for that reason you can implement here rule number 1. Therefore, according to rule number 1, we get that the radius of this circle, we define the radius of this circle as capital R. That is to say, OM, that is the radius of this circle, will be defined as capital R according to our definition. The radius of this circle according to rule number 1 will be equal to the multiplication of the side lengths of the green triangle by each other. That is to say, it is BC times CD times TB over 4 times the area of triangle BDC. Repeat again. Because of the fact that the green triangle BDC is blocked by the circle, we can implement here rule number 1. According to rule number 1, the radius of this circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the green triangle by each other. That is to say, it is BC times CD times DB over 4 times the area of the green triangle BDC. So we get that the radius that we are looking for, the radius of the circle that blocks the green triangle BDC, will be equal to BC. BC equals to 13 units times CD. CD equals to the square root of 61 units. And finally, BD equals to the 6 times square root of 10 units, all divided by 4 times the area of the green triangle BDC. And we already found out that the area of the green triangle BDC equals to 39 units. So actually we answered on this question. Why? Because we found out the area of this circle. In the next step we will just simplify this expression for the radius. That is to say, we will divide both the numerator and the denominator of this expression by 13. So capital R equals to 13 over 13 is 1. So in the numerator we left only with square root of 61 times square root of 10 times 6 over 4 times 39. 39 over 13 is 3. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC will be equals to the square root of 61 times square root of 10 times 6 over 4 times 3, that is 12. Here we will divide both the numerator and the denominator of this expression by 6, and we'll get that the radius of the circle that blocks the green triangle BDC equals to 6 over 6 is 1, so in the numerator we left only with square root of 61 times square root of 10, and 12 over 6 is 2. So capital R, the radius of the circle that blocks the green triangle, equals to the square root of 61 times square root of 10 over 2. Here, according to the algebraic identity, that the square root of A times square root of B equals to the square root of A times B, we will get that the square root of 61 times the square root of 10 will be equal to the square root of 61 times 10, all divided by 2. So capital R equals to the square root of 61 times 10 is 610, so it is the square root of 610 over 2. So the radius of this circle, the radius that we are looking for, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the first method. In the next step I will present to you how to find out the radius of this circle according to the second method. In the second method, we will use before the things that we have already found out in the first method. So here, from point C, we will draw perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. In quadrilateral AB, EC, we have 3 right angles, therefore the fourth angle must be also equal to 90 degrees. The opposite, so quadrilateral ABEC with 4 right angles is a rectangle, and the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6. Therefore, EC will be also equal to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that BC equals to AE, but BC equals to 13 units according to what is given us in the question. Therefore, AE must be also equal to 13 units. Here, the length of line segment ED is equal to AD minus AE. AD is 18, AE is 13, therefore AD minus AE is 18 minus 13, that is 5. So we did all those things in the first method. Now we will continue with the second method. In the second method, from the center of the circle, that is to say from point O, we will go perpendicular on chord BC. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as capital N, and we will define the perpendicular from point O and AD as point M, or the touching point of the perpendicular from point O and AD as capital M. In the next step I will present to you a new rule, and we will implement the new rule in our drawing. Okay, so this will be actually rule number 2. According to rule number 2, so we have a circle. The center of this circle is at this point, point O. And we have here chord BC, that could be any chord. This is chord BC. So from the center of the circle, that is to say from point O, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point O and BC as M. And according to this rule number 2, the perpendicular from the center of the circle to any chord bisects the chord. I write it down. The perpendicular from the center of the circle in this case it is actually point O, is the center of the circle, to any chord bisects the chord. So here perpendicular OM bisects chord BC. That is to say, BM equals to NC. Okay, so whenever you draw perpendicular from the center of the circle to any chord, it will bisect the chord. Here the perpendicular OM bisects chord BC. That is to say, BM equals to MC. So we actually can implement rule number 2 in our drawing. Why? Because in our drawing we have perpendicular OM to chord BC. And according to the new rule number 2, the perpendicular ON bisects chord BC. That is to say, BN equals to NC. I write it down. We can implement rule number 2 in our original drawing, because in our original drawing we have perpendicular ON on chord BC, and according to rule number 2, the perpendicular on chord BC bisects chord BC. That is to say, Bn equals to Nc. Bn equals to Nc according to rule number 2. In the next step, we will focus on quadrilateral ABMN, this quadrilateral. In this quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And therefore quadrilateral ABMN is a rectangle, because it has 4 right angles. Quadrilateral ABMN is a rectangle. But you know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. So AM equals to BN according to the rule that the opposite sides of a rectangle are equal to each other. In the next step, we'll focus on quadrilateral MNEC, this the lower quadrilateral. In the lower quadrilateral MNEC, we have 1, 2, 3 right angles, and therefore the fourth angle must be also equal to 90 degrees. So actually in quadrilateral MNEC we have 4 right angles, therefore quadrilateral MNEC is a rectangle. But we also note that the opposite sides of rectangle MNEC are equal to each other. That is to say, ME equals to NC. ME equals to NC. So actually, to summarize what we did until now, according to rule number 2, we found out that BN equals to NC. BN equals to NC. But we also found out that BN it is not only equal to NC, but BN it is also equals to AM. So we can write here that BN equals to AM also, and we found out that NC is also equals to ME. So we can write here that MC equals to ME, and from this long equation AN equals to BN equals to NC equals to ME, we will derive that AN equals to ME. AN equals to ME. Side AM equals to side ME. Okay. This is point E. In the next step, we will extend line segment AD until it touches the circle, and we will define the touching point of the extended line segment AD in the circle as point F. By doing this construction, we created here called FD. Okay. And we have perpendicular ON to chord BC. ON is perpendicular, therefore it is absolutely a straight line. Any perpendicular must be a straight line. So if we focus on the upper side of the straight line ON on point M, we'll focus on the upper side of the straight line ON at point M. In the upper side of the straight line ON at point M, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 90 degrees, therefore the missing angle to 180 degrees of course. So the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of the straight line ON at point M to 180 degrees, the missing angle must be equal to 90 degrees. Likewise, if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be also equal to 90 degrees, to 180 degrees, according to the same rule. The opposite sides of one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be also equal to 90 degrees. For the same reason. So actually we have here perpendicular OM to chord FD. Why line segment OM is perpendicular to chord FD? Because of the fact that this angle equals to 90 degrees and this angle equals to 90 degrees. So I write it down. So from the center of this circle, that is to say from point O, we have perpendicular OM on chord FD. This is called FD. And whenever you have a perpendicular from the center of a circle towards any chord, it bisects the chord. According to rule number 2, perpendicular OM bisects chord FD. That is to say, FM equals to MD. FM equals to MD. FM, it is actually equals to FA plus AM. So we can substitute FM by FA plus AM. FA plus AM. And it is equal to MD. Here, MD, we can substitute MD by ME plus ED. In conclusion, we found out that FA plus AM equals to ME plus ED. Okay? But we have already found out that AM equals to ME. AM equals to ME. So here, those two line segments are equal to each other, therefore we can cancel them out. And we're left only with FA that is equal to ED. FA equals to ED, here FA equals to ED. But we have already found out that ED equals to 5 units here. So we can only do that ED equals to 5 units. And from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. In the next step, we will extend side AB or side BA until it touches the circle. And we will define the touching point of the extended side BA and the circle as P. In the next step, I will remind you the old rule number 2, and we will implement the old rule 2 in our drawing. According to the old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord FD. This is chord FD that intersects with chord FB at point A. So I write it down. In our original drawing we have chord FD that intersects with chord PB at point A. Chord FD intersects with chord PB at point A. Therefore, we can implement the old rule number 2 in our drawing. According to the old rule number 2, we get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. FA times AD equals to PA times AB. Repeat again, according to the old rule number 2, because of the fact that chord F the intersects with chord PB at point A, we will get that FA times AD equals to PA times AB. FA equals to 5 units, AD equals to 18 units, and it is equal to PA. PA is the missing line segment, so we leave it as it is. Times AB, AB equals to 6 units, so we substitute AB by 6. In conclusion, we found out that 5 times 18 equals to PA times 6. Here we will divide this equation by 6, and we will get that PA, the missing line segment, it is equal to 5 times 18 over 6. So PA equals to 18 over 6 is 3, and 3 times 5 is 15. So we found out that PA equals to 15 units. I'll write it down. PA equals to 15 units. In the next step, I will present to you a new rule. We will implement the new rule in our drawing. The new rule is rule number 4. According to rule number 4, actually according to rule number 4, whenever you have two chords that are perpendicular to each other, you can use a certain formula. So now the drawing for this rule. So we have here a circle that could be any circle. The center of the circle is this point O or point E. The center of the circle is point E. And we have here chord AB is perpendicular to chord CD. That is to say the grade between them 90 degrees. This angle equals to 90 degrees. So according to rule number 4, here the intersection point occurs at point O. So if chord AB intersects with chord CD at 90 degrees. That is to say, if chord AB is perpendicular to chord CD, and they are perpendicular with each other at point O. Then the following equation will be true. Here we define the radius of this circle as capital R. EM equals to capital R. So the following equation, if two chords are perpendicular to each other, the following equation will be true. That 4R square, R is the radius of the circle, will be equal to AO square plus OB square plus CO square plus OD square. I'll repeat again, whenever you have two chords that are perpendicular to each other, then a certain formula will be true. That is to say, so here we have chord AB that is perpendicular to chord CD, and they are perpendicular to each other at point O. Then according to rule number 4, if capital R is the radius of the circle, we will get that 4R square, R is the radius of the circle, equals to AO square plus OB square plus CO square plus OD square. So can actually implement rule number 4 in our drawing. Why? Because in our drawing, chord FD is perpendicular to chord PB. Why they are perpendicular to each other? Because of the fact that in the intersection point they create between them 90 degrees. If this angle equals to 90 degrees. So I'll write it down. Chord FD is perpendicular to chord PB. Therefore, because of the fact that we have here two chords that are perpendicular to each other, we can implement rule number 4. And according to rule number 4, if we define the radius of this circle as capital R, OM equals to capital R according to our definition. So according to rule number 4, we get that four times capital R square, R is the radius of the circle, or capital R is the radius of the circle here, or M equals to capital R, will be equal to FA square plus AD square plus BA square plus AB square. Again, 4R square, R is the radius of the circle, equals to FA square plus AD square plus BA square plus AB square. So 4R square equals to FA square. FA equals to 5, so FA square will be equal to 5 square, that is 25, plus AD square. AD equals to 18 units, therefore AD square equals to 18 square, that is 324, plus PA square. PA equals to 15 units, therefore PA square equals to 15 square, that is 225, plus AB square. AB equals to 6, so AB square equals to 36. So in conclusion, we found out that 4R square equals to 25 plus 225 is 250, plus 324 plus 36 is 360. So 4r squared equals to 250 plus 360, 610. 4r squared equals to 610. We divide this equation by 4 and we'll get that r squared equals to 610 over 4. Here we'll take a root out of this equation and we'll get that r equals to the square root of 610 over 4. That is to say, r equals to the square root of 610 and the square root of 4 is 2. So in conclusion, we found out that the radius that we are looking for, that is to say, the radius of this circle that is equal to capital R equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finished with the second method. In the next step, I'll summarize the lecture. We will start with the first method, of course. So in the drawing we have a circle. We know that the center of the circle is at this point, point O. Line segment AB equals to 6 units. Line segment AD equals to 18 units. Line segment BC equals to 13 units. Angle BAD equals to 90 degrees. And finally, this angle ABC equals to 90 degrees. Our mission is to find out the radius of this circle. So in the first step, we did the construction. From point C we draw perpendicular on AD. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. By doing this construction, we created quadrilateral ABC. Quadrilateral ABC has 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. But AB equals to 6, therefore EC must be also equal to 6. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we'll get that BC equals to AE. But it is given as the equation that BC equals to 13, therefore AE must be also equal to 13. Then we found out the value of line segment ED equals to AD minus AE. That is to say, ED equals to AD, that is 18, minus AE, that is 13. 18 minus 18 is 5. So ED equals to 5 units. Then we joined points D and C together by a straight line. By joining points D and C, we created the green small triangle ECD. Then we implemented the Pythagoras theorem on the small green triangle ECD. According to the Pythagoras theorem, the small green triangle ECD here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle EDC is DC, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to EC square plus ED square. So DC square equals to EC square. EC equals to 6, so EC square is 6 squared, that is 36, plus ED square. ED is 5, so ED square is 5 squared, that is 25. So in conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61. So we found out that DC squared equals to 61. We took out of this equation. We found out that DC equals to the square root of 61 units. This is to say the hypotenuse DC of the small green triangle equals to the square root of 61 units. Then we join points B and D together by a straight line. By joining points B and D, we created the big triangle ABD. We implemented the Pythagoras theorem on the right big triangle ABD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus AD squared. So in conclusion, we can say that in the right triangle ABD, by PT, BD squared equals to AB squared plus AD squared. So BD squared equals to AB squared. AB is 6, so AB squared is 6 squared, that is 36, plus AD squared. AD is 18, so AD squared is 18 squared, that is 324. So in conclusion, we found out that BD squared equals to 36 plus 324. 36 plus 324 is 360. So in conclusion, we found out that BD squared equals to 360. We substituted 360 by 36 times 10. Then we took out of this equation and found out that BD equals to the square root of 36 times 10. The square root of 36 is 6. So in conclusion, we found out that BD equals to the square root of 36, that is 6, times square root of 10. Here, the hypotenuse BD equals to 6 times square root of 10 units. Then we calculated the area of the green triangle BDC. We calculated the area of the green triangle BDC. The area of any triangle, and especially the area of triangle BDC, will be equal to the base of the triangle times the height to the base over 2. I must emphasize that the height to the base must create 90 degrees with the base. So the area of the green triangle BDC equals to the base. We choose the base of the green triangle as BC times the height over 2. The height to the base over 2. So we have to find out the height to the base. In order to find out the height to the base, we extended side BC by a straight line until, and then from point D we drew perpendicular on the extended BC. We define the touching point of the perpendicular from point D and the extended BC as F. Okay, by doing this construction, we created the quadrilateral ABDF. This quadrilateral ABDF has 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABDF is a rectangle. Quadrilateral ABDF is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. AB equals to DF, but it is given us the question that AB equals to 6. So AB equals to 6, and from this equation 6 equals to AB equals to DF, we derive the DF is also equal to 6 units. Here DF equals to 6 units. That is to say the height to the base equals to 6 units. Now we can easily find out the area of the green triangle BDC. So the area of the green triangle BDC equals to the base. The base is BC and it is equal to 13 units, so we substituted BC by 13 times the height. We just found out that the height to the base is 6, so we substituted the height by 6 over 2. So the area of triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So we found out that the area of the green triangle BDC equals to 39 square units. Okay. Then I presented to you a new rule, and we implemented a new rule in our drawing. According to the new rule, if triangle ABC is blocked by a circle, then the following equation will be true, that capital R equals to A times B times C over 4 times the area of triangle ABC. Here we have triangle ABC. Side AB equals to A units in its length, side BC equals to B units in its length, and side AC equals to C units in its length. So, whenever you have a triangle that is blocked by a circle, like in this drawing, what is the definition of a triangle that is blocked by a circle? The definition is that all the three vertices of the triangle must lie on the circle, or must touch the circle. Like in this drawing, this vertex touches the circle at point A, this vertex touches the circle at point B, and finally this vertex of triangle ABC touches the circle at point C. Therefore, we can definitely say that this triangle ABC, it is blocked by this circle, and therefore we can implement here, and whenever you have a triangle that is blocked by a circle, you can implement rule number 1. What is rule number 1? According to rule number 1, this rule number 1, the radius of this circle that blocks triangle ABC, here that is to say OM, that is the radius of this circle that we defined as capital R, will be equal to A times B times C, that is to say the multiplication of the side lengths of the triangle by each other, A times B times C, over 4 times the area of triangle ABC. So we can actually implement rule number 1 in our drawing. Why? Because in our drawing, we have the green triangle, triangle BDC. This green triangle, it is blocked by this circle. Why? Because of the fact that point here, this vertex touches the circle at point B. This vertex touches the circle at point D, and finally this vertex touches the circle at point C. Therefore, we can definitely say that the green triangle is indeed blocked by the circle, and therefore we can implement here rule number 1. I'll repeat again. Triangle ABC is blocked by the circle, and therefore, according to rule number 1, the radius of the circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the triangle by each other. That is to say, it is BC times CD times BD, BC times CD times BD over 4 times the area of the green triangle BDC. BC equals to 13 units, CD equals to the square root of 61 units, and finally DB equals to 6 times square root of 10 units, over 4 times the area of triangle BDC. We have already found out that the area of the green triangle BDC equals to 39 square units. So in conclusion, the answer to the question is that the radius of this circle equals to this expression. Okay, here we just simplify this expression by dividing both the numerator and the denominator of this expression by 13. 13 over 13 is 1, so in the numerator we left only square root of 61 times square root of 10 times 6 over, we have to divide the denominator by 13 also, so it is 4 times 39 over 13 is 3. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC is equal to the square root of 61 times square root of 10 times 6 over 3 times 4. 3 times 4 is 12. So here we divided both the numerator and the denominator of this expression by 6. Here 6 over 6 is 1, so in the numerator we left only with square root of 61 times square root of 10 over 12 over 6 is 2. So in conclusion, we found out that the radius of the circle that we are looking for, the radius of this circle, it is equal to the square root of 61 times square root of 10 over 2. According to the algebraic identity, that the square root of A times square root of B equals to the square root of A times square root, the square root of A times square root of B equals to the square root of A times B, we will get that the square root of 61 times square root of 10 equals to the square root of 61 times 10 over 2. 61 over 10, 61 times 10 is 610. So in conclusion, we found out that the radius of this circle That is to say, capital R equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finish with the first method, then I presented to you the second method to find out the radius of this circle. In the second method, in the first step, we did the things that we have already done in the first method. That is to say, from point C we do perpendicular on AD. That is to say, this again cos 90 degrees and this again cos 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. By doing this construction, we created quadrilateral AB EC that has 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral ABC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side EC, but AB equals to 6, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE, but BC equals to 13, therefore AE must be also equal to 13 units. What is the length of side ED? ED equals to AD minus AE. AD is 18, AE is 13, so ED equals to AD minus AE, that is 18 minus 13, that is to say it is 5. ED equals to 5 units. Then, from now on, we continued with the second method. That is to say, from the center of this circle, that is point O, we do perpendicular on chord BC. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O to chord BC as capital N, and we define the touching point of the perpendicular from point O and AD as capital M. Then I presented to you new rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, the perpendicular from the center of the circle to any chord bisect the chord. The center of the circle is at this point, point O. We have chord BC that could be any chord. According to this rule number 2, the perpendicular OM towards on chord BC bisect chord BC. This is like BM equals to MC according to this rule number 2. You can implement rule number 2 in our drawing. Why? Because in our drawing we have perpendicular ON to chord BC. According to rule number 2, it bisects chord BC. That is to say, BN equals to NC. Repeat again. In our original drawing, we have perpendicular ON on chord BC that bisects chord BC. That is to say, BN equals to NC according to rule number 2. Here, BN equals to NC. Okay, then we focused on quadrilateral ABMN. In quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABMN is a rectangle. Here, quadrilateral ABMN is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Then we focus on the lower quadrilateral MNEC. In quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral MNEC is a rectangle. Quadrilateral MNEC is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So until now, we can summarize what we did until now. According to rule number 2, we found out that BN equals to NC from one side, but from the other side, BN it is also equals to AM. So we can write here that BN equals to AM. Likewise, we also found out that NC it is also equals to ME. So we can write here that NC equals to ME. From this long equation, AN equals to BN equals to NC equals to ME, we will derive that AN equals to ME. Here, AN, AN equals to ME. Actually, it is AM. It's actually AM that is equal to here. BN equals to AM. As you can see here, BN equals to AM. So we can write here that BN equals to AM. BN equals to AM, and from this long equation, we will derive that AM equals to ME. Here, AM equals to ME. This is to say here, AM equals to ME. Okay. So in the next step, we extended line segment DA by a straight line until it touches the circle at point F. And by doing this construction, we created chord FD. Here, ON is perpendicular to BC. ON is perpendicular, it must be a straight line. Okay, so ON is a straight line. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 90 degrees. Likewise, according to the same rule, if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be also equal to 180 degrees. Which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the same rule. So the missing angle here must be equal to 90 degrees. So this angle equals to 90 degrees and this angle also equals to 90 degrees. Therefore, OM is perpendicular to chord FD. Okay? OM is perpendicular to chord FD. Repeat again. Or perpendicular OM on chord FD, according to rule number 2, bisect chord FD. Okay, you can implement here rule number 2. Whenever you have from the center of the circle perpendicular to any chord, it bisects the chord. From the center of the circle, that is to say, from point O, we have perpendicular OM, therefore it must bisect chord FD. That is to say, FM equals to MD. According to rule number 2, FM equals to MD. But FM, it is also equals to FA plus AM. So you can substitute FM by FA plus AM, and it is equal to MD. But MD, it is also equals to ME plus ED. So we can substitute MD by ME plus ED. In conclusion, we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. AM equals to ME. So those two line segments are equal to each other, therefore we can cancel them out. And we left only if FA, that is equal to ED. Here, chord FA equals to chord ED. But chord ED equals to 5 units. So we can write here that ED equals to 5. And from this equation, FA equals to ED equals to 5. We will derive that FA is also equals to 5 units. Here, FA is also equals to 5 units. In the next step, we extended side BA by a straight line until it touches the circle, and we define the touching point of the extended side BA in the circle as P. Here, in the next step, we actually implemented the old rule, rule number 2 in our drawing. What is the old rule, rule number 2? According to the old rule, rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement the old rule, rule number 2 in our drawing. Why? Because in our drawing, we have chord FD that intersects with chord PB at point A. Repeat again. In our drawing, we have chord FD that intersects with chord PB at point A. Therefore, we can implement here rule number 2. And according to rule number 2, we'll get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. Repeat again. FA times AD equals to PA times AB, according to the old rule, rule number 2. FA equals to 5 units, AD equals to 18 units, PA is the missing line segment, so we will leave it as it is, and AB equals to 6. So in conclusion, we found out that 5 times 18 equals to PA times 6. We divided this equation by 6, and we found out that PA equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15. So we found out that the length of line segment PA, it is equal to 15 units. In the next step, I presented to you new rule, rule number 4, and we implemented the new rule number 4 in our drawing. According to the new rule, rule number 4, actually rule number 4 states that whenever you have two chords that are perpendicular to each other, you can use this formula. So, or in other words, you can say also that if chord AB intersects with chord CD at 90 degrees, that is to say they are perpendicular to each other, then the following equation will be true. Capital R is the radius of this circle. The following equation will be true, that 4R squared equals to AO squared plus OB squared plus CO squared plus OD squared. Again, whenever you have two chords that are perpendicular to each other, you can implement rule number 4, and according to rule number 4, 4R squared, and R is the radius of the circle, it is equal to AO squared plus OB squared plus CO squared plus OD squared. We can actually implement rule number 4 in our drawing. Why? Because in our drawing, we have chord FD is perpendicular to chord PB. Why they are perpendicular to each other? Because of the fact that they create 90 degrees at their intersection point, at point A. Therefore, they are perpendicular to each other, and therefore we can implement here rule number 4. Whenever we have two chords that are perpendicular to each other, you can implement rule number 4. So I repeat again, chord FD is perpendicular to chord PB. For that reason, you can implement here rule number 4. And according to rule number 4, we'll get that 4 times r squared, r is the radius of this circle, equals to fa squared plus ad squared plus pa squared plus ab squared. Again, 4 times r squared when r is the radius of the circle equals to fa squared plus ad squared plus pa squared plus ab squared. I'll repeat again. According to rule number 4, 4 times r squared equals to fa squared plus ad squared plus pa squared plus ab squared. Here fa equals to 5, therefore fa squared equals to 5 squared, that is 25, plus ad squared. Ad equals to 18 units, therefore ad squared equals to 18 squared, that is 324. Plus pa squared. Pa equals to 15 units, therefore pa squared equals to 15 squared, that is 225. Plus ab squared. Ab equals to 6, so ab squared equals to 6 squared, that is 36. So in conclusion, we found out that 4r squared equals to 25 plus 225, that is 250, plus 324 plus 36, that is 360. So in conclusion, we found out that 4r squared equals to 250 plus 360. 250 plus 360 is 610. That is to say, we found out that 4r squared equals to 610. Then we divided this equation by 4 and found out that r squared equals to 610 over 4. Then we took a root out of this equation and found out that the square root of r equals to 610 over 4. That is to say, the square root of r equals to the square root of 610, and the square root of 4 is 2. Therefore, we can take out 4. We can take 4 out of the square, and we left only with that the radius of this circle equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.